We have been talking about thermodynamic processes, different type of processes, and then importantly we have introduced the first law of thermodynamics. And to carry on the discussion further, let us talk about certain important thermodynamic processes which we would be needing throughout the discussion of this study of thermodynamics. They are isobaric process. The word bar means pressure. Okay. So, iso means same. So, when the system is kept at a constant pressure, which means that delta P is equal to 0. So, delta P is the change in P and that is equal to 0, which means that P remains constant. Similarly, we call it isochoric process, which is when the system is kept at a constant volume. So, again delta V equal to 0, which means that the volume of the system does not change, as we have seen that this can be achieved by keeping the piston of a container to be at the same position. Then there are isothermal processes where the temperature is maintained, so that there is no change in temperature, once again delta T equal to 0. And also we have talked about adiabatic process. This we have talked about earlier, where no exchange of heat takes place between the system and the surrounding, which is given by this is given by delta Q equal to 0. Okay. So, these are the different processes that would be interested in. Let us go to some of the thermodynamic potentials that will be used in both the studies of thermodynamics and statistical mechanics. We would talk about internal energy, which is mostly if you consider a gas, it is the kinetic energy of the molecules of the gas, and that is the internal energy. We will talk about Helmholtz free energy. It is often written by F, but it is also written by this symbol A in literature. Okay. So, it is mostly written by F, and so we will carry on with this notation. So, F is U minus Ts, where U is the internal energy, T is the temperature in absolute scale, and S is the entropy. We will see entropy in just a while with illustration and what it means in the context of second law of thermodynamics. We also talk about thermodynamic enthalpy, which is nothing but U plus PV is the internal energy plus the pressure into volume. We also often talk about Gibbs free energy. For example, in a superconductor we often talk about this Gibbs free energy, which is U plus PV minus Ts, which means it is H minus Ts, where H is nothing but the enthalpy. And we will also talk about the grand potential, which is U minus Ts minus mu n. This mu is called as a chemical potential and will be discussed later. So, this is nothing but F minus mu n, where F is the Helmholtz free energy. So, these are some of the thermodynamic potentials that will be concerned with throughout the course, and mostly you will see that we will talk about Helmholtz free energy and calculate various physical quantities such as specific heat, compressibility, etc., from these Helmholtz, from the knowledge of the Helmholtz free energy for a given system. So, we also would talk about intensive and extensive parameters, and these thermodynamic systems or thermodynamic quantities, rather the study of thermodynamics really are, they are divided in two categories: intensive parameters and extensive parameters. The intensive parameters are which are independent of the size of the system, and the extensive parameters are proportional to the size of the system, which means that if we double the system, that is double its volume and number of particles, then the intensive parameters they remain unchanged, and the extensive parameters rather they double their values as we double the volume and the number of particles. So, what are the examples of these intensive parameters? Like pressure, temperature, they do not depend upon the size of the system or the volume of the system or the number of particles. Extensive parameters are many, for example, internal energy. So, as you change the dimension of the system, the internal energy increases. S, the entropy, as I said, that we will be seeing it in a while. The specific heat, rather there is the heat capacity and there is a specific heat which is really divided by the CV divided by the number of maybe particles. So, when we scale that with the number of particles, then it becomes an intensive parameter, and volume and magnetic moment and so on and so forth, these are examples of extensive parameters. So, before we get on with the discussion of the second law, let us try to see a logical sort of flow of events. And why it is important is that if I tell you about first law and second law, that is there in all books and all texts that are available on thermodynamics, but there must be a logical way in coming from the 0th law to the first law to the second law and so on. So, just to remind you that the 0th law is about thermal equilibrium. So, if there are a number of systems which are in connected to each other, they would all be in thermal equilibrium with one another. That sets a temperature scale as well as it sort of the thermal equilibrium is being talked about. And then first law is nothing but the conservation of energy. We have seen that, and we have seen that how the internal energy, a part of it is the heat that is given to the system and the work done by the system, and we will see that in more details when we talk about the mathematical formalism of the first law. Now, a lot of systems would actually conform to the conservation of energy, but that does not mean that they would take place. So, this what is written here, that we know from experience that many processes, even if they satisfy the law of conservation of energy, they cannot take place or they do not take place. For example, the water left to itself it will never flow uphill, and if there are two bodies which are made to come in contact with each other, which these two bodies are at different temperatures, then if you leave them alone, then heat would never flow from the colder body to the hotter body, it is always the reverse. So, but they do not in any way these processes that we have said that which cannot happen, they also do not violate the first law of thermodynamics, but we know that they do not occur. So, there must be something else that prohibits them from occurring, and this is embodied in the second law of thermodynamics, which is expressed in two basic forms. In fact, we will tell them in more details. And one form states that a quantity of heat extracted from a system cannot be converted entirely into work. So, the heat that you extract does not completely get converted into work. So, you cannot get the work done which is exactly equal to the heat that is given while leaving everything else unchanged. And this is known as the Kelvin statement. We will come back in the next slide as well, where we formally state these statements that are given by Kelvin and Clausius and so on. Another version of the second law states, which mean the same thing, that heat cannot be transferred from a colder body to hotter body while leaving everything else unchanged, and this is exactly which was there. So, heat never flows from the colder body to the hotter body, and this exactly says the same thing once again, that leaving everything else unchanged. This looks very obvious, looks trivial, but stating them at a time when physics was much less developed was an important step. And this is called as a Clausius statement of the second law. So, these are similar statements, but are stated differently by different people, and let us see these formally how these statements are. But before that, let me define this word entropy quite a priori, but it is important to have this notion, because entropy is the quantity that will govern that which processes, even though they are they conform with the first law of thermodynamics, but actually take place. So, the second law actually talks about the feasibility of processes based on entropy. So, there exists a function of state which we said that is same as the state function, it is called entropy S, and we write it with S, and it is an extensive variable as said earlier. It has the following property. So, during an adiabatic process means that we have delta q equal to 0, or let me write it as dq equal to 0, or even delta q equal to 0. From an equilibrium state alpha to another equilibrium state beta, then the entropy does not decrease, which means that this q in going from alpha to beta equal to 0, there is no heat exchange, and at the most there could be equality between the two, that is S corresponding to the state beta can be equal to S corresponding to the state alpha, S means the entropy, and that happens for a reversible process, and in general for irreversible processes this is the greater than sign exists, which means the system left to itself will never have an entropy lowered. So, here we come to those formal statements that are made by various people, and they are, the classical statement says that no cyclic process exists. Cyclic means in a closed loop, which has its sole effect of transferring a heat from a colder body to a hotter body. This is exactly what we have seen earlier. Kelvin made two statements. One of them says that no cyclic process exists which produces no effect other than extraction of heat from a body and its conversion into an equivalent amount of work. So, we are almost putting it in verbatim. What they have said is that you cannot have extraction of heat from a body and then convert it into work, and this entire heat cannot be converted into work. The second statement of Kelvin said that it is impossible to convert heat completely into work. They exactly are same, stated slightly differently. Kelvin's third statement, which is also known as Carathéodory's statement, it says that different states of a system differing infinitesimally from a particular state, and these states, different states are unattainable, which means that you can't get it from that particular state by any quasi-static adiabatic process. Okay. So, if they are infinitesimally differing from a given state, so this particular state, so these different states are unattainable from that particular state, this particular state that we just talked about in the line above, by any quasi-static adiabatic process. This looks verbose, which means that there are a lot of words being put, but it means something very simple, as we have seen that there are the one is that there will be no complete extraction of heat into work or conversion into work, and the other states that you cannot have heat flowing from a colder body to the hotter body. So, let us analyze these statements, I mean for in our language, in the language of common man, and these statements should be of course equivalent, because if you are talking about the same thing, putting it differently does not make them different. So, they are same. They emphasize the role of entropy, which is hidden, and in defining the sequence of events means that which process is likely to occur and which process is completely prohibited. Okay. So, entropy is the defining parameter, or rather the thermodynamic quantity that decides that whether a particular thermodynamic process will take place. So, if no external agent is doing any work on the system, then the changes in the system can either be irreversible or reversible. Okay. So, the reversible process is accompanied by no change in entropy, delta S is equal to 0, and the irreversible process is accompanied by a change in a definite change in entropy, and a priori this change will always be positive, this change will never be negative. Let us try to see an example. So, consider a red hot metallic ball, very hot, extremely hot, it is immersed into a bucket of cold water. So, if you wait for a while, you will see that the bucket of warm water is in front of you and a warm cannonball. You probably can touch the cannonball and also you can touch the water, but before immersing it into the bucket of water, that is immersing the ball into the bucket of water, it was extremely hot. So, you cannot touch it. Now, after you put it inside the pool of water, bucket of water, it can both became warm. Now, can it happen that if you start with a bucket of warm water and a warm cannonball, we get a red hot metallic ball, and so cannon means a metallic ball. So, this is what we have been talking about, and get a red hot metallic ball and a bucket of cold water? That would never happen, right. There is no agency that can convert a warm ball and warm water to a red hot ball and a cold water. Okay. So, one process is allowed and the reverse process is not allowed, and the reverse process is not allowed because the reverse process talks about a lowering of entropy, and which is not allowed in a system. Okay. So, entropy has to increase. So, it is always accompanied by, and it is an irreversible process, as we just saw, it is always accompanied by an increasing entropy. We will do more examples and problems regarding this. So, finally, what happens is that second law is a universal law of increasing entropy. So, we will do mathematical formulation of first and second laws, okay. But before we do that, let us discuss something very important, and it is often been debated in books of thermodynamics, that what is the real sign convention that one should use for the work done, because you have seen that the first law concerns with work done. Okay. So, we write dW equal to minus PdV. This minus sign is the source of all the debate, and whether there is a minus sign or not, let us see that. So, very strictly we have talked about that this dW is actually not a state function. So, if it is not a state function, it is written with not with a d, but with a delta, but we will ignore that at this moment. When you know that which is a state function and which is not a state function. For example, the internal energy is a state function. Okay. And once again, just to remind you that what is meant by a state function is that when a system goes from one state to another state, how it goes from one state to another, the change in the internal energy is independent of that. It just depends upon u beta minus u alpha. Okay. And but the work done really depends on the path that is followed, which is given by an example earlier. So, how is this the work done? I mean, is it the same work done that we are familiar in mechanics? It is the same work done. I mean, in the sense that P is the only force, it is not really force, that is why it is written within a quote, and this is pressure is force by area. So, this force by area into volume, you see that this has the dimension of work. So, it is force by area, and dV is area into length, and so this area would cancel and you have force into length, and you know that work done is nothing but force into length or displacement, so to say. So, if the system expands, that is you take the piston out so that there is more volume. So, dV is positive, work is said to be done on the system by the surroundings. Okay. And when the system contracts, dV is negative, work is said to be done by the system. Okay. So, it is on the system and by the system. Okay. That is the, this gives rise to the minus sign in the work done, dV is positive. So, minus sign in dW and this will give a plus sign in dW. Okay. So, that is why conventionally there is a negative sign that is put in front of the work done. In fact, in defining this sign convention that just being talked about, the frame of reference is fixed at the surroundings. So, you are looking at the system from outside, okay? And that is why the work done is defined like that. If you actually look at it from the system's reference frame itself, then the work done should be written with a positive sign. And in fact, if you see some chemistry books, they actually use a positive sign, and possibly that the reason being that the change in the reference frame, that is chemistry uses the reference frame to be the system itself, while physics uses surroundings to look at the work done, and that is why it comes with a negative sign. So, coming to the this mathematical formulations, we have seen that it is a du equal to dq plus dw, and as we said that we are neglecting the differences between an exact differential and which is not, I mean, a state function and not a state function. So, using this convention of sign, we have dq minus pdv, and the second law, it is in an irreversible process. The change in entropy is the heat transferred to the system, and this was talked earlier that actually the entropy is nothing but the heat by this ratio of heat by temperature. Okay. And if you think that why is this, if you can write it that ds is equal to lambda dq, which was initially thought that there was no hint that the temperature would come in the denominator. So, one would write it as a lambda, and then it is found that lambda can only be equal to 1 over t, and that is why we arrive at the second law as integral of ds equal to dq by t. And you see that we have not put any limits here. So, it always defines the change in entropy. So, second law only talks about the change in entropy of a system, which is nothing but dq by t. So, if you combine both of them, the first law and the second law, one can write its dq is replaced by TdS here. So, du equal to TdS minus PdV. Okay. So, this is the combined form of first and second law, and it is very useful in solving problems. We will see that. So, there is also challenging the second law, and this was Maxwell actually challenged the second law, and it is very important to understand, you know, that all these celebrated physicists, they started worrying about things when it was at the nascent stage, and they started contradicting each other by coming up with thought experiments or even real experiments and trying to question the validity of various things that were proposed earlier. So, Maxwell challenged the second law of thermodynamics, and he had this in idea that consider a volume divided into two halves, A and B. I just show a part of that here. So, there are A and B, and we have opened a gate here, and there is a daemon that sits here, okay. And the sole work of the daemon is this daemon sitting at the interface, who can open a valve, this valve that we have shown, and let a more energetic gas molecule from the compartment A to compartment B. So, this is a compartment A on the left and a compartment B is on the right, and this daemon, what it does, it selects the more energetic molecule and sends it from A to B. Okay. It is just a thought experiment, and this thought experiment is trying to say that if there is any flaw with the proposal of second law. Okay. So, as a consequence, the internal energy of A becomes less because it is losing energetic particle, and B becomes more. Okay. So, this act of the daemon would cause that to happen. So, thus by letting each molecule fly out of A into B, would further cause this the internal energy of B to be progressively greater than A. So, now it looks like that if that happens, this is going to be a realization of a perpetual machine of the second kind, means the machine that we have just talked about, that converting the entire heat into work. So, this energetic molecules embodies heat, and it is been completely converted into work by this mechanism, and that would violate the second law of thermodynamics. Obviously, it does, but someone called Szilard, he suggested that there is no real violation of the second law. You have forgotten something. What you have forgotten is that the demon is of course opening the valve and letting the molecule fly from A to B. It does work and spend some internal energy. Okay. So, this has to be taken into account with the system, because the demon is interacting with the system by opening the valve and letting a molecule fly in. This becomes a composite part, it is an integral part of the system, and you cannot ignore the presence of the demon. And if that happens, in terms of entropy, we should actually account for the entropy of the demon and then the total entropy which rises, and that would validate the proposal or the statements of second law. So, this delta S is always greater than 0 in the irreversible process. Okay. This is called Maxwell's demon. Let us look at the third law. The third law is also called as Nernst's law. So, we have talked about, if you see it here, that it is really the change in entropy that one talks about in real experiments or real thermodynamic systems. So, is there a way to define, and there is an absolute value of entropy, or how do we actually put a lower limit, and is there a temperature for that, and so on. That is the statement of this third law. So, the change in entropy of a system during a particular thermodynamic process between two equilibrium states, okay, say alpha and beta, they are at the same temperature, and but characterized by different values of another parameter x. We are not specifying what parameter. So, this would tend to 0 as the temperature approaches absolute 0. So, the change in entropy would actually go to 0 as the temperature approaches absolute 0. Let me show you by a picture, and the picture is here. See this. So, we are plotting entropy versus temperature in Kelvin, and these are some other thermodynamic parameters x1 and x2, and these two curves they correspond to two different values of x1 and x2, and you are bringing the system like this, and let us see that. So, the entropy of a system approaches a constant value as the temperature approaches 0 Kelvin. By now, it is fairly clear that entropy is a measure of disorder. So, entropy is the more the disordered system is, the more the entropy of the system. So, at absolute 0, all the thermal motions, they cease to exist, and rendering an ordered state and suggests of a low value for entropy. So, at 0 Kelvin, a system does not contain any heat, okay, and thus all the constituent particles are at their lowest energies. This implies that the system is in a unique configuration, and in its ground state, for which the third law states that the entropy vanishes. This was observed by Nernst in 1906. This means that a 0 entropy state hints at a perfectly crystalline phase and is truly an ideal scenario. An alternative version of the third law of thermodynamics states that it is impossible for a process to bring the entropy of a given system to 0 via finite number of states. So, as you see here, that you are coming at values lower and lower of entropy, the entropy is in the y axis, and you are bringing the system from A to B and B to C, then C to D, D to E, E to F, and F to G, and so on and so forth. So, as you see here, as you come closer and closer to this region, you have infinite number of such small steps with the decreasing step size, and this is what is being talked about, that it is impossible for a process to bring the entropy for a given system to 0, means it has truly a 0 value via finite number of steps. You need really infinite number of steps. So, another form of the statement can be framed as for a system undergoing a reversible isothermal process, the change in entropy approaches 0 as the associated temperature tends to 0. So, this is what we are talking about, this graphical representation of the entropy, is that as a function of the temperature it will be helpful in understanding the essence of the third law. So, let us fall back on this diagram that we just shown. The constant energy processes are the horizontal lines that you see here, the horizontal lines BC and DE and so on, because they are at 0 entropy, that is change in entropy is 0. So, corresponding to lowering of temperature by changing certain thermodynamic parameter x between x1 and x2. This thermodynamic parameter can be anything other than, of course, this entropy and temperature, it could be pressure, volume, and so on. We are not specifying that. So, it will require infinite number of steps to achieve t equal to 0. So, as you come closer and closer to t equal to 0, these number of these steps will increase with decreasing step size. So, important applications of the third law mainly include understanding of the behavior of system at very low temperature, and it yields support to the first two laws, that is first law and second law, laying down a foundation, strong foundation to the concept of entropy. The entropy being 0 at absolute 0, and a finite number of processes is insufficient to achieve absolute 0. So, this line here, the last two lines, they sum it all about the entropy and the third law.